So welcome to this lecture on advanced digital system design in the course digital system design with PLDs and FPGAs. The last lecture we have started with the effect of metastability in sequential circuit and data path. We didn't spend much time on how the metastability happens in a flip flop or latch or anything like that, though briefly I mentioned the cause of it in a gist. Essentially our focus was to look at the effect of metastability in sequential circuit and data path and how to handle that situation so that the proper operation of the circuit is not impaired. Definitely analyzing the metastability in detail, starting with the cross couple latch, moving to kind of edge triggered flip flop and all will bring clarity, but due to lack of time we will set that aside and focus on the what is useful for the design of the digital system. We will handle it, that is a plan. So let us run through the slides we have looked at the last lecture. So we know that in an edge triggered flip flop, for the data to appear at the output from the input data has to satisfy some timing requirement with respect to the clock edge, active clock edge. The data has to arrive sometime before, that is called setup time. Not only that, it has to remain at the input after the clock edge for a while, that time is called, the duration is called hold time. If that happens, then from the clock edge with a delay the output appears, okay. And this I said, if you analyze a master slave flip flop from which this edge triggered flip flop is constructed, during the negative for a positive edge triggered flip flop, during the negative clock period the master is in transparent mode. So the setup time would normally mean from the active clock edge, that is from when the master is going to be cut off from the input, actually the minimum time required for that latch to set, because that is when the latest the input can change. If afterwards if the input changes, there is not enough time to set the master latch. So that is what is the setup time. Of course normally in the clock path there will be inverters to choose the correct polarity and to choose the opposite edge for the slave and all that. So normally there will be 2 inverters. So that inverter skew has to be removed from the setup, and the whole time is that inverter delay itself, because even after the clock going high it takes that inverter delay for the master to cut off, that is a hold. So during that time the data should not change, and when the positive clock edge comes, the slave get the copy of the master, slave is enabled, the master is disabled. So for the time for slave to set is the propagation delay. Normally again there will be an inverter, that delay has to be added with the latch delay, slave latch delay for the propagation delay. So that is the essence of this setup, hold and propagation delay. But again in a basic course many times you are told that if this is met, the input is captured at the output kind of truthfully, but many times it is not discussed what happens if it is violated, okay. So many things can happen, as we said. If the setup and hold time is violated, the flip flop can miss trigger. That means suppose the previous value was 0 and was trying to set to 1, it may remain in 0 or it may kind of set to 1, okay. Now so it means that you are not really sure what the output is going to be. It could be 0 or 1, but as I said, normally it is not a dangerous situation as long as input persists for at least 2 clock periods, then definitely in the next clock edge everything will be okay, because it will meet the setup and hold time, and then the data is captured at the output properly. Okay. So mistriggering itself is not a very serious issue, but the second effect is that it might take longer time to resolve it. That means if the data changes close to the active clock edge, it will take long time for it to settle, and that is dangerous, because like we have in a sequential circuit we find the minimum clock period, and once you decide that, if the data the output takes longer to settle, then it can violate the setup and hold time at the destination register. No issue with this flip flop, but it is driving something at that destination register. It can upset the setup hold time, and the worst effect would be that this output can get stuck to a voltage level which is not neither 1 nor 0, it will be in between, and that can drive the any circuit, not even flip flop, it can even drive the combination circuit into active region, the gate, and that will act as amplifier. Any slight noise it will start switching, it will dissipate a lot of power. Maybe it is taken care in the design depending on how you design, but definitely this is quite disastrous that it gets stuck in between. And the worst thing is that we cannot definitely say when it will come out of it, we can only say about the probability. So that means it can remain there for a long time. When we talk about probability, that does not kind of preclude chances of it getting stuck for a say 5 seconds or 5 minutes or anything like that. Though we talk about the probability, you should remember that, but that happening often when the probability is low may not happen, but then like the probability is probability, so you should not have kind of a deterministic view on the probabilistic events, that should be kept in mind. So let us come to that, the effect of it. But in a sequential circuit or in a data path, we take care of all these. We choose the proper clock period to meet the setup time. We analyze the effect of the skew, we analyze the effect of hold time, and the skew effect on both we will consider, though we have not discussed that in our lectures, but we will be doing that when I take the FPGA part of the course. So in a data path we do the maximum frequency analysis, hold time violation. Similarly in a FSM we do both, and then when the metastability can happen in this circuit is a question, and we said yes, there could be inputs directly coming to this combination circuit in a data path. There could be inputs coming to the first stage of the data path, maybe this continues, there is registers, combination circuit, registers, combination circuit, and so on. But at some point somewhere some data from the external world or the data path comes in, and in an FSM there are inputs, mainly this is from the data path, but we are not sure the frequency of the clock from where this input is coming. Okay, it may not be same. So, or it could be some process which is generating a logic value like a limit switch, which has no relation with the clock many times, and then these inputs may not meet the setup and hold time. As far as this input is concerned, it may not meet the setup and hold time, and as far as this is concerned, it may not meet the setup and hold time. This latency, as I said, is a matter of shifting. It does not affect the probability of any particular input getting creating metastability in this flip flop. Similarly about this. So the problem as far as a sequential circuit or a data path is concerned, the asynchronous input is the one which can cause metastability. So once again, though we have learned metastability, our concentration as far as sequential circuit and data path is concerned, should be on inputs which are not synchronous. Okay. So if you are a good designer, that there you should focus your attention. The inputs coming from an asynchronous domain, okay, that should be handled properly. That's where the crux of the problem, okay, that's like asynchronous inputs. So when we say asynchronous input, it will be an input which is generated as a on a flip flop or a register with a different clock or a process which is not synchronized to the sequential circuit. So very easy to answer this question, that the problem is that the input is asynchronous. So the solution is to synchronize it, and it is again we don't know, probably at the beginning you don't know how to synchronize, but it's very easy. Suppose there was an asynchronous input which was going to this combination circuit and reaching a destination register. The way to synchronize is that you connect that input, asynchronous input, to a D flip flop clocked by the same clock as the sequential circuit, and the Q is connected here. Now what happens is that the D is captured by this and appears with a delay. Now anytime D changes, this is captured at the Q with a delay of propagation delay TCO, and that transmit through the propagate through the combination circuit reach here. So if the clock period is chosen properly, in the next positive edge here, this input, that means the output of this synchronizing flip flop, will meet the setup time, and whole time there should not be a problem. And of course the input which is synchronized will reach at this destination register with a latency or a delay of 1 clock period. So that's a penalty we pay, penalty in terms of time, that there is a latency, and penalty in terms of the area which is a flip flop. Okay. So nothing comes free, so you suffer in delay and suffer in the area, okay, that you should know. Now as I said, we have not solved the problem in a very kind of foolproof way. Earlier there were chances of all these or some of these flip flops getting into metastability. Now there is no guarantee that this will meet the setup and hold time of this flip flop, because this is asynchronous with respect to this clock. So this can get into metastability. Okay, now that is better than the earlier case, but like we are kind of sampling the asynchronous input in one point, but earlier it was sampled by different flip flops, and maybe some will get into metastability, some will not, some will mistrigger. It was a mess. Okay, it was you couldn't say what is the kind of what is happening at the output. Some could be 1, some could be 0, some could be in metastability and so on. Okay, though the way I say, you might think that it occurs so frequently, it doesn't. Okay, but that's I want to highlight the problem of sampling an asynchronous input at multiple places with different path delay. Okay, that's the issue. But our hope is that if this synchronizing flip flop get into metastability, by the next clock edge, if it comes out of it, and if there is enough time for it to propagate through combination circuit and meet the setup time at the destination register, it's okay. Okay, so that is the real hope. But like this I want to state, I can only kind of make a statement. We are not going to analytical part of it. The fact is that the probability of a flip flop remaining in metastability decreases exponentially with time. That means if this synchronizing flip flop get into metastability, as the time passes, the chances of it coming out becoming exponentially more. So every nanosecond you give extra, it's an exponential increase in the probability of it coming out of the metastability. Again I warn you, it is a probability, I mean it is not certain, like you cannot say after you give 1 nanosecond extra it is surely now with a double chance it is going to come out, it may remain there. Okay, there is a kind of logical problem in the last sentence, but like I hope you got the picture. So the idea is that we give enough time for the synchronizing flip flop to come out of the metastability, in which from now onwards we can analyze that part. The time available for it to come out of metastability is that in this part there is a clock period, one clock period, a clock comes and before the next clock edge this output should reach here. But now if it get into metastability it should come out, propagate and meet the setup time here. Okay. So how much time is available for it to come out of metastability, that is the total clock period minus this time for the propagating through the combination circuit minus the setup time, at least by then it should come out. Okay, suppose the clock period is 10 nanosecond, setup time is 1 nanosecond and the combination delay is 4 nanosecond. So the put together it is 5 nanosecond. So we are hoping that within 5 nanosecond after getting into metastability this comes out of it, then there is no issue, everything goes clean. But that also tells us that if we are able to give more time like then there are more chances of it coming out of metastability. So it is a question of analyzing it, finding the probability and checking is that okay, like not only the probability, maybe we have to convert that into the rate of metastable kind of failure, metastability failure in the sense that it does not come out of metastability, or the average time between such failures. Okay. So if it is large enough and if it occurs very seldom then it is okay. Okay. So but if that is not okay, like you have the metastability resolution time for a single stage is t clock minus t com minus t setup, then we have to increase it. We cannot kind of at least from the outset we should not tamper with the clock period. If you reduce it the system will suffer. So we reduce this combination circuit and we are trying to make it 0, and that is by by putting another register in a chain here, so that the output of this flip flop see only a flip flop, not a combination circuit. So that is double stage synchronizer. So we put 2 flip flop. Now the time available for this to come out of metastability is clock period minus the setup time. Okay. But the price we pay is a 2 clock period latency. So if something happens here, the worst case it will appear here after 2 clock period. Okay. That is and of course in terms of area 2 kind of flip flops. Now suppose if like you kind of assess the probability and find that it is not enough, the mean time between failure is not very large, then we will be forced to kind of increase the clock period, but then this should not be affected. So what we do is that we divide the clock for this part and retain the original clock for this sequential circuit or the data path, main data path. So that is what is shown here. So you divide by n, the clock is coming from here, the main clock goes to the sequential circuit, divided clock goes to the synchronizer, and now we have the clock period is n into t clock, because we are dividing by n, then the clock period increases by n minus setup time. So that should normally solve the problem. N is, and now the latency is 2 clock period of the divided clock, which is nt clock. So 2 nt clock is a latency which can be high, but n itself is 2, 3 or 4, things like that, not a huge number. But I said there is an issue here of a skew, because there is a skew between this clock and this clock. The source register's clock is a delayed version of the destination register clock. So like if you put the destination clock like that and the source clock is coming delayed, okay, so that eat into the available clock period. So the available clock period for the propagation will be T clock minus this Q. So this Q will force one to increase the clock period, okay, that's not a good idea, and we will definitely analyze the effect of skew in the clock period, all that in the whole time violation and all that in different scenarios. You know, there could be different scenario depending on which side the clock comes from. So we will analyze all that, but at least I want to tell you the problem here. So what we do is that to avoid that we put a D skew flip flop, because now the skew come between two adjacent flip flop without any combination circuit. So it's kind of, you know, T clock minus Q should accommodate the TCQ and the T setup, which will be much smaller than this, will be much smaller than this, which is like this. Suppose if there is a skew here, the situation is it's going to eat into the clock period and it is going to push the clock period up, okay. So this wouldn't, and that is the D skew flip flop. Definitely it will add latency to the whole process now. So it will be the latency you can work out, it's a 2n T clock plus the T clock, because this is not clocked by this kind of output of the counter, but the input of the counter. So that is what we have looked at the last class. I have repeated it because it's important, that should get into your mind very clearly, and this is a kind of standard solution. Almost people treat it as a kind of thumb rule. Wherever they see an asynchronous input, they put 2 flip flop in a chain, sometimes they put 3 flip flop, okay, we will see why 3 flip flop. I don't quite agree with such kind of thumb rule, which is like many a times if you ask some people, like you're sampling an input, say the Nyquist rate, how many times you should sample, they will say 10. This 10 is not a magical number, you know that we have 10 fingers in the hand. So we use a decimal system, maybe because we have the 10 fingers in the hand, because earlier the counting was you know, based on the fingers, and we will keep a tally for how many tens, and that is how the decimal system you know, kind of arose. And before that people were like, even for now, for the time we use 12 as a base. So there were like duodecimal number system was there. So what I am talking is that my argument is that if we had 12 fingers, then we will be all the time telling 12, rounding off to 12 everything. So just relying on thumb rule for design is a very bad thing, and nowadays anyway it doesn't work, because people want very optimized circuits in terms of area, power dissipation, delay and so on. But you should, as a designer, you should not resort to these kind of the magical tricks which is told by other people to do that. Whenever you see an asynchronous input, 2 flip flops or 3 flip flops without any questions asked, not a good idea. At least when you are working in a CMOS technology, you know the kind of the delays you can expect in that technology, and from there you go back and analyze. It is the data is difficult to come by for metastability analysis, but I am hoping that you can get it, at least look at some the published work on that, and you know, assure yourself that the scheme you put is enough, or it is not kind of, you are not over designing and so on, like where you the 2 double stage is enough, don't put multiple cycle synchronizer and so on. So let us come back to it. Instead of multiple cycle synchronizer, sometimes people put a kind of cascaded synchronize. That means they will put 3 flip flop in a chain, 4 flip flop in a chain and so on. The argument is that like say you can work out the probability, like if you know the the frequency of the clock and the setup and hold time window width, and if you know the rate of change of the asynchronous input, because this need not be kind of regular square wave. So the average rate or the maximum rate, whatever, depending on, average rate should be good enough to take, and then you can find out the rate of metastability entry. Then knowing the time, that the fact that it will, as you give more time, the probability of it coming out increases exponentially with time. So the probability of it remaining there decreases exponentially with time. Okay. So from there we can find out what is the rate at which the second flip flop can get into metastability, and again do the same analysis for the second flip flop. Then you know what is the rate at which the third is kind of getting. But so this, you know that the probability gets multiplied and the chances are becoming less and less for you know, when you come towards the real sequential circuit, the probability of that the last flip flop getting into metastability is very less. So the mean time between failure will be huge numbers in terms of maybe millions of years. That should be good enough for large number of products which you make out of that design. Okay. So that's a basic idea about the cascaded synchronizer. The probability of metastable output reduces multiplicatively. That means that remaining in metastability reduces multiplicatively at each stage of the cascaded synchronizer. So some people do this instead of, and it doesn't matter, you know, to be very frank, like here, like if you assume 4 flip flops, okay, so you have a latency of 4 here, okay, and you are using kind of 4 flip flops, and if you go back to this and you put a divide by 4 counter, mode 4 counter, then use 2 flip flop, the latency is 2n t clock, which is nothing but the 4 clock cycle of this. So essentially kind of things are you know, similar, there is no difference. It is a matter of kind of some choice. Only thing is that maybe this introduces a skew, but in the cascaded there is no skew. So many times when you see some kind of solutions, at least the theoretically sometime it all means the same, though the argument, the structure is different. So one should look at it and try to make sense out of it. Okay. Now let us look at the effect of asynchronous input to FSM. Now I must warn you, saying that there is no reason for you not to synchronize an asynchronous input in a very serious design. Maybe this concern is little bit old, where one used to use kind of discrete kind of devices where a flip flop can be very costly. Maybe putting 2 flip flop will end up, you will end up using a kind of 20 pin or 24 pin DIP package which occupies. But nowadays the SoC chips are you know, it's so small and there is so much density of transistors or gates, not a problem, not much of a problem. But then it is nice to analyze, at least academically we learn something in a complex situation, what is the effect of the asynchronous input. That is the only thing. So I would suggest that if there is an asynchronous input, synchronize it rather than applying these techniques which I am going to say. So assume that this enable is an asynchronous input to a state machine, and the state machine is like that. As long as it is low, remain there. If it is high, transit to this state with 1 1. Now mind you, there are 2 flip flops, Q1 and Q0, and now the situation is that we are not synchronizing. This asynchronous input is going to the input of Q1, that flip flop, and the 0th flip flop. Okay. Now because of the path delays, difference in path delays, this will be sampled at different point in time, and you can imagine sometime it may happen that the Q1 transit to 1 and Q0 remain there because it is asynchronous, or the opposite can happen. the Q1 remain in 0, that means mistriggered, it retained the previous value, but the Q0 has transited. So it may happen that instead of the valid state 1 1, when the clock comes it transits to an kind of invalid state 1 0 or 0 1, and we don't know about this state, and this could be kind of some state within the state diagram, or it could be unused state, whatever it is dangerous. This is not like output races where it goes briefly there and come back, it really mistriggers. So you can imagine that you have a very complex state machine which loops and branches and all that. Suddenly you find that it is in some state, and soon you find that the state machine is elsewhere and it continues from there, and it is quite dangerous. So you should never suppose if you are not synchronizing, the solution is not to do such a kind of assignment. You should make it grey code so that only one of the flip flop change. So even if there is a mistrigger, it does not matter, either it will remain 0 0 or it will transit to 0 1. So always do a go or no go, like enable bar remain there, enable go there, but this should be grey coded if you are using an asynchronous input. The similar situation can happen when the state machine is in say 0 0 and enable is an asynchronous input. When it is 1 you transit to 0 1, when it is 0 the machine transit to 1 0, okay, the state machine transit to 1 0. Now since once again, since it is we are talking about in this condition when enable is 1, Q0 is changing the state, when enable is 0 Q1 is changing the state. Now you can imagine that this 2 flip flop sampling the one input with different path delays. So it may happen that one instead of both changing, one might change. So you are hoping like here here only the Q1 was changing, here only the Q0 was changing, but Q1 will kind of interpret it as 1 and will change, and Q0 also will interpret it as 1 and change. Then you will end up in another invalid state, and this is quite dangerous. Again the solution is that never branch on asynchronous input like this, like when it is 1 go to some state and 0 goes to other state. You should always adopt a go no go structure. When it is 1 transit, when it is 0 remain there, and this should be grey coded. And as I said, always it is even better to synchronize the asynchronous input without much botheration, unless it is a very small circuit you are trying to. Suppose you are making a 4-bit counter and you have an up down input direction input from somewhere, and if you double synchronize the up down and direction, then that will end up using 4 flip flop which is equal to the counter flip flop. So but these situations are rare, and if at all you use a 4-bit counter it will be a very small application. So that you should kind of remember. So better to synchronize the asynchronous input. Related to it, so now essentially what we have covered is the how to handle what is metastability, what is its effect on a flip flop, and in a sequential circuit and data path how it affects, and how to where the problem really come in a sequential circuit or in a data path. And we said the problem is asynchronous input, the solution is to synchronize it. So we have looked at the single stage synchronizer, double stage synchronizer which improves the reliability or the probability aspect is improved, then multiple cycle synchronizer or cascade synchronizer, and we have seen what happens if you use asynchronous input in an FSM to make branching, okay. So we have seen one branching with multiple flip flops changing at the same time, and one branching where depending on that input it make a decision to go to one side or the other side. So that is what we have seen. Now a related kind of scenario is this, something called reset recovery time, okay, and that is related to the asynchronous reset in a flip flop, which is a kind of this recovery time. The notation is TRC, like TREC is a recovery time, or TRR, okay, the RR and REC is the subscript. So essentially this you would not have kind of realized or learned, and nevertheless it is a very important aspect. You would have assumed that at least the behavior of an asynchronous reset in a flip flop is that you assert that, you make it active, with a delay the Q goes to 0 and you remove it, then the clock comes, everything works fine, is what we assumed, okay. But there is a factor called recovery time. That means that the reset recovery time is a minimum amount of time between the deassertion of this signal and the next clock edge, active clock edge. Suppose the clock is coming, the positive clock edge is coming here, the reset should be removed sometime before that, okay. Otherwise this output can get into metastability, okay, and this is quite serious because in a digital circuit there could be tens of thousands of flip flops, okay, or hundreds of thousands of flip flops, and many a times at the power on a single reset tree can reset all the flip flops, okay, most of the flip flop, and it has to be reset because precisely same reason. There is no guarantee that if you power on all the flip flops, all the outputs are going to be neat, you know, like during the power on probably it can get into metastability. So reset is essential, but if you don't meet the reset recovery time in flip flop, again the metastability can happen in the flip flop. So this is something which is overlooked, and many times one think of the assertion of the reset, not the deassertion, that is a problem. Like we are not asking the right question. When you assert it, fine, the reset is driving the internal latches, you know, that's the problem. Like in an edge triggered flip flop you have a master latch and a slave latch, as I said, that is, and this reset, asynchronous reset, is directly going to the master latch and slave latch and resetting it, and you can look at the circuit diagram for it, then you will realize why that happens, okay. Again in this course I do not have time to go into the details of that because it will eat up into our time. So when that means they are driving the master and slave latch directly, not going through this clock gating, you know, that is why it is asynchronous. As soon as you assert with a delay, this is reset, the output is reset, the clock does not matter because it is going directly into the latch, and what the clock does is that it gates the input to the master latch and so on. So we are bypassing that, but now when you remove it, it may happen that you are kind of this is being, input is driving the master latch and it is nearing that setup time, it is close to that minimum time required for it to set up, and you are messing it with through the reset. It is trying to set through the D, and we are removing it, we have driven it to 0, but we are removing it very close to the clock edge. So then this will not have enough time to set it up. So this should be and how much time is not the setup time because this is directly going to the latch. So this is the kind of reset recovery is the time delay of that path where this reset is going and kind of resetting the latch. Okay, that path, like if you analyze a detailed circuit you can find a reset recovery time in terms of the gates involved and so on. Okay, but I hope you get a picture of the situation. Okay, that's a problem, like you can assert at any time, with a delay it will be kind of reset because it directly going, it doesn't matter. But when you remove it and it is near the positive clock edge, near the setup time, then this thing can get into metastability because 2 drives are there and this doesn't have enough time to drive it to the proper value. So this can get into metastability. So this has to be met, and that is now so you would see that most people, most vendors or designers would advise you to use synchronous reset because it is safe. Okay, but there is an like nice feeling about asynchronous reset, saying that like the outputs, the flip flops are reset without a 1 clock period delay, because in the case of synchronous reset there could be the worst case 1 clock period delay for it to reset. Okay, so if you want to reset something very quickly even before that for whatever reason, maybe for kind of reliability, fault tolerance or critical situation, whatever, this may be good. So now understanding the reset recovery, what is the solution? Okay, now if you say kind of okay, let's synchronize asynchronous reset, then it is like synchronous reset only, because what synchronous reset do, we do it outside. It really it meets this kind of reset recovery time, but then it is a synchronous reset. The behavior is synchronous because you assert the reset, it comes with a 1 clock period delay, or worst case 1 clock period delay. It is like the synchronous reset, but we can say this with certainty. So let us not synchronize the leading edge, but let us synchronize the trailing edge, because if you don't synchronize the leading edge, as soon as you assert it the reset happens, and the problem is about removing it near to the clock edge. So if you synchronize to the clock edge, it is removed after the clock edge and it will definitely meet the recovery time at the next clock edge. So that's the idea. So that is what I have written here. To retain the asynchronous reset behavior, only the trailing edge of the asynchronous reset should be synchronized. So that's a game. So I am showing straight away a possible kind of solution. There are many other, but I am showing the again the simplest one. So assume there is a power on reset circuitry which has no kind of relation to the clock. It comes, so if it is kind of going to the asynchronous reset of flip flop, then it can cause metastability. So we are synchronizing it. So this is a synchronized version of the reset. It is an active high reset signal, as the name suggests. It is active high, and you can imagine that this part is a delayed, the worst case 2 clock period delayed version. So now the trailing edge comes much later. Now what we are doing is that we are ORing together. Okay, so what happens is that leading edge come as it is, because it is ORed with the delayed version, but the trailing edge is synchronized version. So that is the clever trick for a active high reset. Now the same technique, I hope you got this. We have a double stage synchronizer for the power on reset. So this is a synchronized version, but both the leading and trailing edges are synchronized. Now what we do is that we kind of OR the original reset, so that we get the leading edge as it is. Okay, so it's kind of ORing of a pulse with a delayed version of the pulse. So you get the leading edge as it is, and the trailing edge is a synchronized version which comes with a late kind of worst case latency of 2 clock period. Okay, now for the active low signal, that means this is kind of like it goes in the opposite direction, is 1, then it goes 0 and it come back to 1. So we replace this AND OR gate with an AND gate, then we have done it, okay. So it's a kind of 0 and a delayed version of 0. You know that for the AND gate any input is 0, the output is 0. So it is like as far as the active low signal is concerned, we have studied at the beginning. If you remember, we have looked at the difference between AND function and AND gate, okay. Now this is an AND gate doing an OR function for an active low signal. So for an AND gate the inputs and outputs are active low, then it's doing an OR function, and we have discussed this in the overview when we have kind of done a review of the basics. We have done that, and that is basically, I have told at that point in time, that is bringing in the De Morgan theorem into our concept, okay. So this is the circuit for active low reset, and naturally when in a chip there are a lot of flip flops to be kind of reset. So it's not a good idea that one wire drive everything, you need to kind of buffer it properly for because the fan out is limited. If suppose the fan out of a gate is kind of say 50, then if there are 1000 then you need 20 buffers, and now you have to balance it out. It's not a good idea that you put a buffer, then you drive 20, then again you buffer it. So everything get delayed in a chain. So you do a balance buffering, and this goes to however many you want, you put it parallelly, and these branches drive out subsections of the circuit, okay. That is what is shown here. So essentially what we have looked at in the last few slides are the reset recovery time, which is related to the metastability. This is related to the asynchronous reset of a flip flop. Since the asynchronous reset is kind of driving the internal latches directly, if there is no problem in driving it, but while removing it, if the clock edge is kind of is near to the clock edge, then that is the setup path, setup time of the input that can kind of interact with this drive and cause metastability in the output of that flip flop. So the solution is to synchronize, but then it does not have an asynchronous behavior. So again we said it's fine if we synchronize the trailing edge rather than the leading edge, and the solution we have looked at is that let us synchronize it but do an OR function, okay. So in the case of an active high reset we use an OR gate, and for the active low reset we use an AND gate, and that was the solution. So kind of I wind this metastability synchronization part here. So the essence is that when you find an asynchronous input, you have some idea of what is the mean time between the failure with regard to the metastability, or when you encounter the asynchronous input, and do the synchronization. And we have not handled all possible ways of doing synchronization, but this is by far the most useful part, at least for a basic course. I think that should be good enough. And of course the reset recovery, again we have discussed what to do, but this has to be applied kind of without any hesitation whatsoever, okay. So that you can blindly kind of replicate whatever I have told. So let us move on. With this I have kind of, I am winding up the digital design part of my course. I have given you how to do a hierarchical top down design. We have seen an example of a CPU, then we have looked at what is data path, what is controller, what is the controller behavior, what is the structure, how to design that structure, how to design a control algorithm, whole methodology we have seen, and we have looked at a case study where everything is applied. All these principles are applied very maybe not a very complex case study, but it was a kind of real life case study. We have looked at all the practical steps. Then we have looked at the various issues in the finite state machine like power on reset, clock frequency, output raises. Then we have looked at the problem of state assignment, unused states. Then we have looked at how to reduce output delay by decoding from next state logic, by encoding the output in the state bits, all that. And then we also have come to this problem of metastability in flip flop, asynchronous input, synchronizing it, reset recovery. So kind of I have covered and I have given a kind of a review of your basic basics you have learned in the undergraduate course so that you are familiar. So I think with this you should be able to kind of make a good design, and we will take case study. Now we have learned VHDL, we are kind of completing that, and now what is remaining is the two devices, device technologies, the programmable logic devices and the field programmable gate array. Okay, now once I complete that and bit of VHDL, we have not covered the test bench, then we can kind of look at the case studies where we play with the tool, we implement that on a board. I don't have too much time to show you lot of case studies and so on, but then I will show something that should be enough. And nowadays the people are kind of solving lot of problems, like say in mathematics the people try to solve all kinds of problems, and yes, that's good because that makes you quick and that works out in examinations where in a short period of time you are able to solve more number of problems. But in real life many a times that is not the situation. That is not that in a fraction of a second you have to solve a problem. Okay, you have to solve a problem creatively, elegantly, without much cost, without causing harm to the humans, environment and things like that. Okay, and so if when you work out some example case study, that should have the real life element in it. It should address all the basic issues involved, so that then very few case studies are enough instead of doing a lot of projects. There are some people resume is full of projects, and that they have done this, they have done that, but nobody asks how come in a short time somebody is able to do so many projects and understand it well. It is better you do fewer projects, fewer things with a greater grasp and kind of come out with the creative solution, the elegant simple solution. The elegance, when you say elegant, it's a qualitative word. We cannot kind of put numbers, how to assess something is elegant, but then it appeals, that solution appeals, something is elegant, the music is elegant, the way somebody kind of dress is elegant, or when you look at the nature it is kind of beautiful, and that can be applied. That's a little bit qualitative aspect, but then we are able to judge that something is elegant or not. So that is just a kind of not justifying the fact that I am not able to kind of do lot of case study. I can do it, I have enough, maybe I can kind of do a course full of case study, there is no issue, I have so much stock with me. So that's not the point, but that doesn't educate you, increase your depth of knowledge and so on. So I am trying to balance it out. Now I am trying to stress on the device technology, the programming language. Even with the programming language I have emphasized what it means, what this construct means, and what equations it creates, what logical structure it creates and so on, rather than simply dwelling on all kinds of syntax and all kinds of jugglery with the syntax. there's no point, there is for for an expert person even a simple tool would suffice. You have a very good photographer, he is able to take a good photograph with a maybe a simpler camera, but given to a novice even the most advanced camera he will not be able to do that. That is true with any tool. So the sophistication of the tool wouldn't guarantee that what you design will be kind of efficient, elegant, fault tolerant and all that. That comes with expertise, the creativity and the logical thinking and systematic working and all that. So that you should keep in mind. So my plan is now to complete this programmable logic devices. I didn't start it because we will be stuck in between. It might take 2 or 3 lectures. So we will handle the evolution of it, the historical evolution of it, the simple PLDs which are very rarely used nowadays, but maybe there is a use in some cases for it, and there is a complex PLD again the application is limited. Then we will have one part of the VHDL which is remaining is the test bench, and there is another part called functions and procedure. If time permits I will take it, but it's one part of the language wherein it is very similar to a sequential programming language. Of course there is something called operator overloading which is related to synthesis, but with whatever I have discussed you can kind of grasp it. Then we will go on with the FPGAs, then we will play with the tool and the case studies, and that should kind of wind up put everything together and give you a complete picture of designing the digital system practically, and it will equip you to kind of start in the path of digital design. I wouldn't say that will kind of make you an expert in the front end VLSI design or front end FPGA design, but that's a good starting point so that you can continue, you can learn, you can practice and do well. So please now like we have covered almost 2/3 part of the course, the last part is coming up, so please review whatever we have done. Learn well. I wish you all the best and thank you.